Good morning to you all. I'm Vongai, and my topic is on improving the shelf life of baby leafy salad vegetables. First, I'm going to give an introduction of what leafy vegetables are, and then I'm going to explain the few experiments that I've done on surfactants and explain future work. Leafy salad vegetables include lettuce, spinach, broccoli, tatsoi, and others. And their consumption is on the increase because consumers are becoming more aware of their nutritional value, and also they are available all year round and ready to eat, so they offer convenience. However, there are a few challenges. For example, maintaining product safety, and the other one is that they are highly perishable, so their shelf life is very limited. Next, I'm going to explain the experiments I've done on surfactants. So, what are surfactants? Surfactants are surface active compounds that reduce the surface tension between either two liquids or between a solid and a liquid. You may wonder, why did I have to focus on surfactants considering my topic? We've been working very closely with our industry partner, Houston's Farm. And they expressed that sometimes there is a challenge, for example, like when it's too windy or very rainy and there's a lot of grit or sand on the leaves. Sometimes it's difficult to wash them off with the sanitizer only. So my task was then to try and identify a surfactant that is on the list of permitted additives and washing agents, which can help in the removal of grit. And this is very important because, as you can see, the two consumers on the screen are not very happy. So when the leaves have some sand on them, consumers don't like it. So the aim is to also keep the consumers happy and to maintain good product quality. The overall objective of this first experiment was to investigate the effect of sodium dodecyl sulfate, which is a surfactant in question, and peroxyacetic acid, a sanitizer, on grit removal, microbiological safety, as well as shelf life. So in this trial, I had 6 different treatments. That is, tap water is our control, and peroxyacetic acid, 40 parts per million. And I tested surfactants at 2 different concentrations, that is 0.05 and 0.1%. And the other treatments were a combination of the surfactant and the sanitizer. So the first step was to homogenize the leafy salad vegetables. So now I'm going to show you a video of how I would do the processing in the lab. Okay. So first I would wash the leafy vegetables in the treatment solution for 45 seconds, and then use the salad spinner to separate the leafy vegetables from the wash water. And I would make sure that I rinse off any grit or soil left on the salad spinner. And then I would spin the leafy vegetables in the salad spinner to get rid of any excess moisture. And then add the remaining solution and grit to the container containing most of the liquid. And then I would keep the wash solution for further tests that I'm going to explain next. And then package the leafy salad vegetables in Ziploc bags for microbiological analysis and also for a mini shelf life trial. Okay, so these are the tests I conducted on the wash water. I would measure the pH, that is the degree of acidity and alkalinity, and measure the turbidity of the wash water and the oxidation reduction potential. And it measures the ability of a solution to either oxidize or reduce a substance. And I also measured the amount of peroxyacetic acid for the PA solutions. And then I would filter the wash water and then dry the filter papers and quantify the amount of solids that were washed off from the leafy vegetables. I also conducted microbiological analysis of the leafy vegetable. For this experiment, mainly I was working on spinach. So next I'll show you the results, but you'll notice from the screen that I didn't show the results for turbidity. This is because when I measured the turbidity of the solutions before washing and also after washing, I noticed that even before washing, the SDS itself also affected the turbidity of the solutions. So it wasn't going to be a good indicator of the amount of solids washed off. From the screen, you can see that peroxyacetic acid solutions had a much lower pH, that's acidic, around 4, whereas peroxyacetic acid solutions and tap water had a higher pH, that is almost neutral. The oxidation reduction potential of peroxyacetic acid solution was much higher, which means it's an oxidizing substance because the values are positive. And with higher PAA concentrations, the oxidation reduction potential also is higher. And for the SDS solutions, the ORP values were low. And you can see that the peroxyacetic acid concentration before wash and after wash is not that different. Okay, now I'll show the results for grit removal. So as we can see, 0.05% washed off more solids as compared to tap water. But what was interesting was that peroxyacetic acid actually washed off less solids as compared to tap water, which seems to suggest that the sanitizer actually reduces grit removal. But as soon as we add the surfactant, we find that the amount of grit removed actually increased. However, less solids were washed off by 0.1%, and this was unexpected. So the next experiments were to try and understand this anomaly. Then in terms of the microbiological results, we can find that regardless of the treatment, there was a small log reduction, less than 1 log reduction observed when we compare the samples collected before wash and also after wash. But however, comparing the different treatments, there was no significant difference between all the treatments. And then this graph is showing the results for microbiology results for TVC of the wash water. And as we can see, the count for the wash water from the PAA solutions was actually less than for the SDS solutions and tap water. This shows that peroxyacetic acid is playing an important role in keeping the wash water clean and preventing cross-contamination. Okay, the objective of the next experiment was to quantify the effect of increasing SDS concentration on grit removal, microbiological safety, and as well as shelf life. So for this experiment, I tested 2 different varieties: spinach, because mainly it represents most of the varieties which are flat, and coral, which represents most of the varieties which are curly. And I tested 3 different concentrations, that is 0.025, 0.05, and 0.1% SDS. And from the results, you can see that increasing SDS concentration results in a slight increase in the amount of grit that is removed. As you can see, the amount of solid washed off for coral is higher than for spinach. But however, we cannot safely conclude that more solids were washed off from coral, because it's also possible that since they were grown in different beds, maybe the amount of solids on coral was more originally compared to spinach. Compared to spinach. Then in terms of the TVC counts, again we see that between the treatments there was no significant difference. That's the same as what we observed from the results for spinach. And then in terms of shelf life, we noticed that for the leafy vegetable stored at 0.1, treated with 0.1% SDS, particularly spinach, after 8 days of shelf life, already there were signs of wilting compared to the other leafy vegetables treated with SDS at the lower concentrations. And also the amount of foam for the SDS, so 0.1% SDS solutions was a bit more, so that might also affect the taste of the product. So for my next set of experiments, I will only use 0.025%. So I will have 4 different treatments, that is tap water is my control, and then peroxyacetic acid at 50 parts per million, and SDS is 0.025%, and also a combination of peroxyacetic acid and the surfactant. And I will conduct this time more elaborate shelf life study, which will involve measuring of the physical chemical properties, that is color, texture, chlorophyll, and vitamin C. And I'll also do microbiological analysis of the TVC and also Pseudomonas. And also I'll have a panel of 5 members who do a sensory evaluation of the products during shelf life. Then my other work will be on temperature control. Why is it important to worry about controlling temperature along the supply chain? Mainly because temperature affects the rate of enzyme catalyzed reactions like respiration, transpiration, and degradation of color and texture. And also it affects the growth of microorganisms. So I will monitor temperature along the supply chain from harvest to storage on the farm, processing, transportation to the distribution center, and also retail storage and retail display. And this will be to Queensland, and also I'll monitor temperature even locally here in Hobart, following the supply chain. And then as a follow-up experiment, first I will conduct shelf life studies across different ranges of temperature. So I'll store the salad bags at different temperatures to try and establish that if I store the bags at this temperature, what will be the shelf life. And then I will come up with a model and validate the model. And then I will store the salad bags at following the temperature fluctuations recorded during the supply chain trial, in order to try and quantify how much we lose of shelf life based on the fluctuations that the product experiences. And during the shelf life trials, I'll also be assessing the physical chemical properties, the microbiology, as well as conduct sensory evaluation. Then my other work will be on vacuum cooling. As you can see from the picture, this is an example of a vacuum cooler that we have at Houston's farm. And vacuum cooling involves placing produce in a vacuum chamber and then lowering the pressure. This results in evaporation of moisture from the product, resulting in cooling. So a lot of moisture is lost from the product. So nowadays, hydrovac coolers are becoming more popular because they result in less loss of moisture from the product. And the main advantage of using vacuum cooling is it results in quick removal of field heat, and it's very suitable for leafy vegetables because they have high surface area to volume ratio. So the study will mainly involve evaluating the benefits of vacuum cooling on shelf life. So in other words, I will test different varieties and then store some of the leafy vegetables under conventional cooling, the ordinary cooling in the cold room, and then expose some of the leafy vegetables to vacuum cooling first, then followed by the conventional cooling to try and establish if there's much benefit in vacuum cooling. And some authors suggest that vacuum cooling may result in internalization of pathogens. So this is something that I also investigate to see if vacuum cooling will affect the efficacy of washing the leafy vegetables in sanitizers. I would like to extend my sincere gratitude to Woolworths and our industry partners, Houston's Farm, and our staff from Tasmania Institute of Agriculture, and our ARC chief investigators, and my fellow PhD students. I thank you all for your attention.